All right, guys, so today we are going to kind of just blow our way through chapter 10. There's only 2 sections, but each section covers a lot of little topics. It's kind of like, let's take everything from geometry and throw it at the wall, and we'll just see what sticks. So a lot of this, I'm going to walk you through a lot of example problems. There's a lot of formulas that you're going to need to use. I'm not worried about you memorizing the formulas. That's something that I will give you on the homework, on the test, on everything that you need to succeed in the class, but you do need to know how to use the formulas. So the first thing that it introduces in chapter 10 is angles. And this one should be a pretty quick review for most of you. If I were to take a circle, and if I start at this center, there are 360 degrees in a full circle. So if I were to travel all the way around my circle, I would go 360 degrees. So when it asks you to measure an angle that subtends or spans the circle, what it's saying is, what's the angle measure that goes, when it says a semicircle, it's talking about the angle of half of the circle. So instead of going all the way around, I'm only going halfway around. Well, if all the way around is 360 degrees and I'm going halfway, I divide that by 2 and I get 180 degrees. So a semicircle is 180 degrees if we're measuring in degrees, okay? A quarter circle, again, instead of going all the way around the circle, I'm only going a quarter of the way. So I'm going to stop right here. So if I take 360 degrees, and a quarter is breaking it into fourths. So I can either divide by 4, or I can take 360 degrees and times it by a fourth. Either way, I'm going to get the same answer. I'm going to get 90 degrees. Okay? And that's one that we should have memorized at this point in our life. Most of you know that a quarter circle is about 90 degrees. C, an eighth of a circle. So again, I'm not going all the way around the circle. I'm only going an eighth of the way around the circle, which is right about there. So if I take 360 degrees and I times that by 1/8, which I think is sometimes easier than dividing, then really I'm just taking my fourth and I'm cutting it in half. So that one is 45 degrees, okay? An eighth of the way around the circle is 45 degrees. Now, 1/100th of a circle. I'm not going to draw it because my picture's already a little bit messy, but instead of going all the way around my circle, I'm going 1/100th of the way. So I'm going to times this by 1/100, which comes out to be 360 over 100, which is 3.6 degrees. So 100th of a circle is just 1/100th, 1/100, times the full circle, 360 degrees. Okay, moving on. Again, I'm going to give you all these formulas, so don't stress about memorizing them. It might be a good idea to copy them into your notes so you don't have to keep referring back to the video, but you will have access to these formulas. This diagram right here, it gives you the different shapes that we're going to be using: circles, squares, rectangles, parallelograms, and triangles. And then the first column gives you the formula for their perimeter, and the second column gives you the formula for the area of that shape. And not only that, but I like this diagram because when it uses the variables, it draws them on the picture for you. So like, look at the parallelogram. It tells you the width is this angled line right here, and the length goes across the bottom, and the height is the height of the parallelogram straight up and down. So it's not the length of the side, it's the height of the shape. So then when you get your formula for the area over here, it tells you length times height, L times H. So using these formulas, this window question, you have probably seen this half a dozen times in your life. It's been a popular one since I was in school, but it tells you that there's a window that consists of a 4-foot by 6-foot rectangle capped with a semicircle. How much trim is needed to go around the window? Now, we are going to assume that the trim doesn't have any width itself. So really, it's just asking what the perimeter of the window is. And we need to be a little bit careful because even though we've got these formulas, I mean, really, this part right here, this is just, I've got a rectangle, right? And it's 4 feet wide and 6 feet tall. And then I have a semicircle on top of that rectangle. And my diameter of my semicircle is 4, going all the way from one side to the other. Now, even though I have these great formulas, if I'm not careful about using it and knowing what I'm using, I'm going to get in trouble. I know that the perimeter of a rectangle, it tells me right here, perimeter of a rectangle, nope, that's area. Perimeter of a rectangle is 2 of the lengths plus 2 of the widths. Well, if I call this my width and this my length, that becomes my width and this is my length. But I've got to be careful. I'm not going all the way around the rectangle. I'm just going around 3 sides of the rectangle. So instead of using that formula, I'm just going to add up those 3 sides. So I've got 4 plus 6 plus 6. I'm not adding that side because it's inside the window. Now I have a semicircle. And I need the perimeter of the circle so that I can find the perimeter or the circumference of my semicircle. So to find perimeter, I take pi times diameter. So pi times diameter, which my diameter is 4 because that's the width of the window right here. So pi times 4, we just write that as 4 pi. But I don't want to go all the way around the circle. I only want to go halfway around the circle, right? So instead of 4 pi, I've got to cut that in half, which just gives me 2 pi. So I'm going to take 4 plus 6 plus 6 plus 2 pi. And that gives me, what, 16 plus 2 pi? Now, depending on how the question asks you for an answer, this is a great answer to me. But if it wants you to round, you're going to have to do 16 plus 2 pi on the calculator, and then just be really careful that you round correctly. But if this was something on paper and it wanted an exact answer, that right there would be a great one for me. Okay, another example. You've built a stairway of a house, and it wants you to cover the space beneath the stairs with plywood. So rather than being able to go under your stairs, it wants to cover that opening with this triangle of plywood. Now, I have a little bit of an issue with this diagram because it doesn't tell you that that's 90 degrees, but it does tell us that the height of the triangle is 9. So this would be my height. This would be my base, right? So to find the area of a triangle, we take the base, which is 12. We times it by the height, which is 9, and then we have to divide that by 2. Don't forget that you have to divide by 2 because it's not really what we do when we do base times height is we turn it into a rectangle. But we're not doing a rectangle, we're doing half of a rectangle, so we divide it by 2. So your answer is going to be 54. Well, and I guess we should probably use our units correctly. 54 feet squared because we're dealing with area. Okay, City Park. I like this question. I wish it didn't give you the diagram. Otherwise, I think this would be a great ACT question. It says that there's a city block and it's bounded by 2 sets of parallel streets. The streets along the block are 55 yards long. So most people are going to draw this as a square and say 55, 55. But then it tells you that the perpendicular distance between the streets is 39 yards, which means that I don't have a square. I have a parallelogram. And this is 55, this is 55, but my distance, my perpendicular distance right here is 39. So if you go back to your formulas, here's my parallelogram. To find the area, which is what we need because we're going to cover it with how much grass, right? That's what sod is. My area is my length times my height of my parallelogram. So if I go down here, I've got my length of my parallelogram is 55. My height of my parallelogram is 39. So I'm going to do 39 times 55, and I have no idea what that is. No, we don't need to sign in. 39 times 55, we're at 2,145. So 2,145 yards squared. That's how much grass it's going to take to cover that park. That's a lot of grass. All right, three-dimensional objects. So we're just, again, quick review of 3 dimensions. Our surface area is the area of the surface of the shape. That's why it's called surface area. So we're trying, it's still in square units, but you're looking for kind of how much, it's kind of like a box. The area is how much cardboard it would take to make the box. The volume is how much stuff you could fill the box up with. Okay, so these are, our units are going to be cubed when we're talking about volume. Our units are going to be squared when we're talking about surface area. And again, I'm going to give you these formulas. You don't have to worry about memorizing them, but it would probably be a good idea to write them down so that you have access to them for the homework. All right. So a water reservoir. A water reservoir has a rectangular base. Now, one thing, if you've ever had a class from me before, and we have done geometry in that class, I like pictures. I think it's foolish to try and do geometry problems without a picture. So as it tells me that my base is a rectangle, I'm going to draw my base as a rectangle. And it says it has vertical walls that are 15. Oh, sorry. My base is 30 by 40. And it has vertical walls that are 15 meters high. So the walls of my shape here are 15. Whoa, that was a bad rectangle. So these are 15 high. At the beginning of the summer, the reservoir was filled up. At the end of the summer, the water depth is 4 meters. So at the end of the summer, I'm not all the way full. I'm only up 4 meters. So instead of a height of 15, I'm only 4 meters filled. How much water was used? Oh, this is a good question. We're going to have to do a little bit of math here. First of all, it wants to know how much water I used. So I have a few options. I could find the volume of the entire shape and then find the volume of what's left and subtract it. Or I could just find the volume of this shape. If I just find the volume of what was used, I don't have to do subtraction. So if my height was 15 when I started and now it's only 4, that means I have used 11 meters worth of water as far as my height goes. So my height right here is 11. Now to find the volume of a rectangular prism, that's right here. Volume, I need my length times my width times my height. Well, my length is 40, my width is 30, and my height, because I'm only looking for the top that has been used, I'm going to times by 11. So 40 times 30 times 11. So if I go 40 times 30 times 11, I get 13,200. So 13,200, and we are in meters. So meters cubed is the amount of water that was used. Okay. You could have found all of the water and subtracted what was left, or just subtract to begin with and just find what water got used. Scaling laws. All right, so this one we got to be a little bit careful of. This might be new for a lot of you. The way scaling laws work is, we kind of talked about this a little bit when we were talking about advertisements trying to mislead or data trying to be misled. So what's happening is, if I am making something twice as big, okay, if I'm taking an object and I am making it twice as big, scaling laws tell me that the lengths will scale with the factor. So something that was 4 feet long is going to now be 8 feet long because I'm timesing it by 2. I'm doubling it. That's my scale factor. If I'm working in 2 dimensions, my area, if the area of my shape was 40 feet squared, then when I double it, when I double my shape, I don't just times by 2. I have to times by the square of the scale factor. So in other words, lengths are just going to be your regular scale factor. Areas, you have to times by your scale factor squared. So if my scale factor was 2, now I have to to find my new area, I have to take 40 and times it by 2 squared, which is 40 times 4, which is what, 160 feet squared. And if I want to find my new volume, if my object is doubled, if my scale is doubling, then I'm going to find my new volume, I take my scale factor and I have to cube it. So let's say that my object, whatever it was, if I had 300 feet cubed, if that was my volume, if I'm going to double that object, to find my new volume, I double it, but I have to change my 2 to the third power because I'm working in 3 dimensions. Volume is 3-dimensional. So this has to become 300 times 8, which is going to be what, 2,400 feet cubed. So be really careful with scale factor. So here's some examples. If you were to double your size, how does that affect your scale factor? Well, first of all, your scale factor is 2. But if I'm going to double my size, let's look at what happens to the different parts of me, right? So by what factor has your waist size increased? Well, waist size, if you look at the distance around your waist, that is just a distance. That's one-dimensional. That is just a length. So my waist size, part A, is just going to double. It's just going to times by 2 because that's my scale factor and I'm just working with length. How much material am I going to need for my clothes? Well, if you think about your clothes are definitely not one-dimensional, right? Your clothes are 2-dimensional. They have an area. So if I'm doubling myself, if I'm timesing by 2, to get my new area for my clothes, I have to square that 2. So my scale, my factor for my area is going to be 4. I'm going to quadruple my clothes. By what factor has your weight changed? Well, if we call weight volume, which I have a little bit of an issue with, but that's what the assignment's asking us to do. If my weight is the volume, how much mass do I have? Well, volume, we said we had to raise our scale factor to the third power. So I've got to do 2 to the third power, which is 8. So my weight is going, if I double in size, my weight is going to go up. I have to multiply my weight by 8. So if I weighed 200 pounds to start with, and I doubled in size, now I'm going to weigh 1,600 pounds. Theoretically, again, I have some issues with that, but that's what it's referring to as volume. Okay, so that is homework 10A. It's a little bit more than I expected, a little bit longer. We do have to cover this in one day, so I'm just going to keep going to 10B. If you want to pause the video right here and work on homework 10A, that would probably be a good idea. We are going to do 10A in class, and I'll be available to answer questions to help you there. 10B is all about a whole bunch of geometry that you're never going to use, but it's stuff that you might see and hear, and it wants you to understand kind of what it's talking about. So the first thing that you're never going to use, but you're going to see in your life, is converting measurements of degrees from just fractional degrees to minutes and seconds. So for example, if I were to say that my angle is 3.6 degrees, a lot of people, and in some branches of the military, in some branches of science and physics and engineering, they don't like decimal fractions or decimal or fractional degrees. They use what is called minutes and seconds. So basically, if I have 1 degree and I break that up into 60 parts, each of those are called minutes. Okay, so 1 degree breaks up into 60 minutes, just kind of like 1 hour breaks up into 60 minutes. Same idea. Each of those minutes breaks up into 60 seconds. So just like with time, except for instead of hours, we are going to start with degrees. But it's the same idea. 1 degree breaks up into 60 minutes. Each of those minutes breaks up into 60 seconds. And what this does is it helps in some branches of physics and engineering and science. It takes these inaccurate measurements, these angles, and it just makes them more precise, okay, without having big, ugly, long decimals. So, for example, converting 3.6 degrees into degrees, minutes, and seconds. So I've got your solutions right down here for part A. It says we take 3.6 degrees, which is equal to 3 plus 0.6. And we convert that 0.6 into minutes. So to do that, I take 0.6 and I multiply by 60 minutes because each of those degrees has 60 minutes. Well, 0.6 times 60 is 36 minutes. So I would say that 3.6 degrees is equal to 3 degrees and 36 minutes. You'll see this a lot, well, and even in the moving on when we start talking about, again, a degree, if you think about like the Earth, it's 360 degrees around, but each of those individual degrees is hundreds and hundreds of miles. And so it makes sense to want to break 1 degree into a smaller, easier measurable unit when you're looking at comparing a distance on Earth to the degree that represents of the Earth, all right? Now, going backwards, if I wanted to go from 30 degrees, 33 minutes, and 31 seconds, what I'm going to do is I'm going to take my 30 degrees and I'm going to add 33 minutes. But to get that 33 minutes, I need to convert that into degrees. So instead of timesing by 60, which is how I turned it into minutes, I've got to divide it by 60. And then I'm going to add my 31 seconds, but instead of the way I turned it into seconds was by dividing by 60, dividing by 60. So now I've got to, timesing by 60, timesing by 60. So this time I've got to divide by 60 times 60 instead of multiplying by 60 times 60. And when I do that, oh, look, it's got the decimals for me right here. It's approximately that 30 degrees right there, that little approximate symbol means that these aren't exact. So we're adding about 0.55 degrees, and then we're adding about 0.00861 degrees. So we are approximately 30.55861 degrees. And if you look at that measurement compared to this measurement, you can see why some people might like to use minutes and seconds when they're measuring large objects in degrees. Okay, latitude and longitude. Again, something that you've been dealing with for a long time. Latitude, remember, latitude is how far north or south of the equator you are, okay? So 10 degrees north of the equator means that you are going from the equator. If you were to look at the center of the Earth, you've gone up 10 degrees, okay? 90 degrees north of the equator is the North Pole. 90 degrees south of the equator is going to be the South Pole, right? Now, longitude is our east and our west, and we start at the prime meridian, which is drawn right here on the globe for you. And again, we can go 10 degrees. We can measure our distance west or 10 degrees east. But notice a couple of things. At the equator, as I go, the way that I'm moving north and south, I'm going up, and in this diagram, we're increasing by 30 degrees on each of these lines. There are smaller lines in between. But with our our longitude and with our east and our west, we start at the prime meridian. And if I go this way, I'm going west. If I go the other direction, I'm going east. Right? If you imagine that you were standing right here looking at the earth, you've got east and west. And it's going to ask us to do some math with these facts, okay? Which is going to take, again, it's math you're probably never going to use, but it's just something you might see here and be exposed to, and it wants you to have some foundation with it. So suppose that you could drill from Miami straight through the center of the earth and continue to the other side. All right, so I actually covered up Miami right here. So Miami is, let's see, Florida looks like we're right about here, right? So here's, it gave us Miami right there. There's my latitude and longitude. At what latitude and longitude would you emerge? Okay, so if I'm traveling through the earth, we've got to be a little bit careful. The way that this works is in order to find my new latitude, all I do is switch from north to south. Okay, if I'm going through the center of the earth, my new latitude is my old latitude, but I switch north and south. So Miami is at 26 degrees north. So straight through the earth, if I were to go straight through the center of the earth and come out the other side, my new latitude would be 26 degrees south. Okay. Now this is not, I repeat, not how east and west works. Okay. My new longitude is, if I'm at 80 degrees west, and I think it's easier to tell like at a lower longitude, like imagine that I was right here at 30 degrees west. I can't just go 30 degrees east because 30 degrees east is like right here. It is definitely not through the center of the earth and coming out the other side. It's right here next to me. So the way that longitude works is you have to take 180 degrees and you minus your old longitude, and then you switch your east and west. Okay, so with Miami, my old longitude was 80 degrees. So I take 180 minus 80, and I get 100 degrees. So my new longitude is 100 degrees, but I used to be west, now I am east. So that's a little bit hard to remember. The north and south, super easy. You just switch whether you're north or you're south. The east and the west does not change so easily, okay, because it goes around a different center of the earth. And if you look at the lines, they're different, right? The east and the wests go from the North Pole to the South Pole, and then they all reconnect to themselves. Our north and south lines, they don't ever connect to each other because they're moving up. It's like slicing a watermelon in half instead of a cantaloupe, which we cut from the top to the bottom. Okay, let's look at part B. Part B says if you dug a straight hole through the United States, you'd come out in China. Well, let's look at that. If I go straight through the earth from the United States, well, it tells me that, let's get rid of some of this. This is messy. I can't see what's going on. All right, so the United States is, let's just kind of pick right here at the center of the United States. So we'll say that the United States, and that's probably not quite the center, but we are at about 30 degrees north, and our longitude is what? We'll say 115 west. So if I go straight through the earth and come out the other side, my new latitude is going to be 30 degrees south. And my new longitude, I take 180, I minus 115, and I get 65. 65 degrees, and I used to be west, now I am east. So if I think about China, if I'm going, let's see, 30 degrees south, that puts me down here in the southern hemisphere of the earth. And 65 degrees east, I mean, China, guys, China's like right here. It's in the northern hemisphere, very much northern hemisphere. And it's definitely not at 65 degrees east. 65 degrees east is like Europe. So we don't dig a hole through to China. But that's a good thought. You might come out more, it looks like we're going to come out more at like New Zealand or Africa. I don't know. Okay, part C. Suppose you travel through, this is a good question. 1 degree of latitude. How far have you traveled? So basically what it's saying is if I'm walking along the earth and I walk 1 degree, how far have I gone? Like, what is that distance? Well, all the way around the earth is 25,000 miles. And I'm just traveling 1 out of 360 degrees around the earth. So if I divide that by 360 degrees, so let's go 25, 1, 2, 3, divided by 360, I get about 69.4. So 1 degree of the earth, if you were to walk that distance, is about 69.4. And what units am I using? Miles? So if you drive 70 miles, you've driven about 1 degree around the earth. So 1 degree represents about 70 miles. Suppose you travel through 1 degree of longitude, either east or west. How far have you traveled? Well, it's the same. Going around the earth straight, going around a line of, I guess we've got to be careful. Whether I'm going north or south all the way around the earth or east or west all the way around the earth, I'm going that same distance. All right, I think we covered what we needed to there. Angular size. Again, guys, something you're not going to use, but it's one of those that you may hear or see at some point. Basically, if an object is closer to your face, it seems bigger. And what angular size is there's a little diagram right here that's trying to show it. The angular size of a coin is, if you were looking at a coin, what would the angle be from the top of the coin to the bottom of the coin? Well, obviously, as the coin gets farther away, that angle gets smaller because it's farther away. So that angle that you're looking at the coin from, that angle gets smaller. And again, it's just a formula that we're just going to have down. So the farther away an object is located from you, the smaller it's going to appear. Here is our formula. Angular size is equal to the physical size multiplied by 360 degrees divided by 2 times pi times the distance. We are not going to go through what it takes to create that equation. We're simply going to use it, okay? So if a quarter that is 1 inch in diameter, approximately how big will its angular size be if you hold it 1 yard from your eye? We're not going to use 1 yard, we're going to use inches. So my angular size is equal to my 1 inch physical size times 360 degrees divided by 2 times pi times my 36 inches that it is away from my face. So doing some quick math, 360 divided by 36, that's 10 over 2 pi, which is just going to be 5 over pi, which is going to be a smaller decimal. So 5 divided by pi, 1.5915. So the angle that your eyeball would see that coin, if it was a yard away, that angle would be, what was it? I already forgot. 1.59. Okay, this angle right here is 1.59 degrees. Be really careful that you use the same units for the size and the distance. Otherwise, it's not going to work. The angular diameter of the moon is approximately 0.5 degrees. So the angular size is 0.5 degrees. And the moon is approximately 380,000 kilometers from Earth. What is the real diameter of the moon? Oh, that's a cool question. So I'm looking for the size of the moon. And I know 360 degrees, I know 2, I know pi, and it gives me the distance. Instead of giving me the size, it gives me the distance. And I'm trying to find the size. So that means I've got to take this fraction right here, and I've got to move it to the other side. Now, if you remember when you're dealing with fractions, I can multiply by the reciprocal. So all I need to do is 0.5 multiplied by this upside down, by 2 pi 380,000, all divided by 360. So 0.5 multiplied by 2 times pi times 380,000, right? 380,000. That gives me my top, but then I got to divide that by 360 degrees. So the diameter in kilometers of the moon is 3,316. So the diameter of the moon is 3,316-ish kilometers. Okay, 2 more. I know, it's a lot of little topics, a lot of little equations, a lot of little formulas, but don't stress, we'll give it all to you. This all deals with slope, okay? So this car's going up a hill. We can say that the pitch of that hill is the height of the hill divided by the length that the car traveled. That's called pitch, okay? So that would be 2 over 20. The slope of the hill is the exact same thing. It's 2 over 20, which is 0.1, okay? We just say it differently. When we say pitch, we say 2 in 20. When we say slope, we say 0.1. We actually divide it. When we say grade, what is the grade of the road? We take that 0.1 and we write it as a percent. That's it. So suppose a road has a 100% grade. What is its slope? Okay, well, 100%, if I turn that into a decimal, it's 1. So it has a slope of 1, which means its pitch is 1 in 1. You go over 1, up 1, over 1, up 1. That's the pitch. What angle does it make with the horizontal? Now this one, that's rude. We haven't talked about that. But if I'm going over 1, up 1, over 1, up 1, over 1, up 1, hopefully you recognize that that angle that you made right there, that is 45 degrees. Okay, if you're going over 1, up 1, you're going 45 degrees. Which is steeper, a road with an 8% grade or a road with a pitch of 1 in 9? Okay, well, 8% is 0.8. 1 in 9 is 1 divided by 9. So we're going to say 1 divided by 9. 0.111111. So which is steeper? Which one of those numbers is bigger? The 0.111111. So the 1 in 9 is a steeper road than the 0.8. Which is steeper? A roof with, oh no, 0.8, it's 0.08. Bad math, Mr. Reed. 0.08, which is still smaller than the 1 in 9. As I'm looking away, I'm like, wait a minute, 0.8 is bigger. That's because it's 0.08. Which is steeper? A roof with a pitch of 2 in 12. So 2 in 12, I'm just going to turn this into slope because it's so much easier to compare slopes. So 2 in 12 is going to be what? 1.6666 or 0.2, not 2 in 16, 2 in 12. 0.1666. So 2 and 12 is 0.16666 forever. 3 and 15 If I turn that into a slope, 3 divided by 15 is a fifth, which is 0.2. So which one is bigger, 0.2 or 0.1666? So the 3 and 15 has a steeper pitch. All right, Pythagorean theorem. 2 more and we are done. The Pythagorean theorem, we're not going to read through this. You guys have used this for years. Hopefully it's one that you have memorized. If you have a 90-degree triangle, the sum of the squares of the A and the B, the two sides, is equal to the square of the hypotenuse, C. So, to find the area in acres of this shape that it gives me, it tells me that my hypotenuse is 1,200 and my A or my B is 250. So 250 squared plus B squared equals 1,200 squared, right? Well, I can't find the area until I find this side because I need to do base times height. So I'm going to do B squared equals 1,200 squared minus 250 squared, which means B equals the square root of 1,200 squared minus 250 squared. Distance, we're just solving for B. So if I go second square root, 1,200 squared minus 250 squared is going to equal 1173.7. So we'll say this is 1173. What did we say? 7? 0.7. 1173.7. All right, so let's double check our math. We're good there. We're good. So now in order to find the area, I've got to find, right now I'm just dealing with feet, right? So to find the area, I do 250 times that new number, and then I divide it by 2. So there's my new number. I'm going to times it by 250, and then I'm going to divide. No, I'm not. I'm going to divide by 2. And I get 146708. 146708. That's feet squared. But it wants me to convert to acres. And 1 acre equals 43,560 feet. So let's divide that by 43,560 feet squared. And that's going to give me how many acres? So 43 divided by 43,560. Divide 43,560. 3.367. So 3.367 acres would be my final answer. I know I went fast. Rewind, pause if you need to. Go back, watch it again. Slow motion, although I might sound kind of funny if you do it that way. Okay, similar triangles, and then I promise we'll finish. 2 triangles are similar if their angles are the same and if their sides are the same ratio with each other. So in other words, you are tripling or quadrupling the triangle or timesing all of the sides by the same amount. It's just a scale factor of the other sides. But the angles don't change, okay? So for this triangle right here, we're going to use proportions. And the way that we're going to do this is I'm looking for A. I don't know what A is, but I know that A prime, my other triangle, that same side is 4. And I know that B on my original triangle is 9, and B on the new triangle is 6. So A over 4 equals 9 over 6. So if I cross multiply and divide by 6, 4 times 9 is 36, divided by 6 is 6. So that means A is 6. Now to find C, well, I know that C on the old one is 12, but I'm looking for C on my new one. So I've got to use one of my other shapes. My old B was 9. My new B is 6. So as long as I'm putting the old on the top and the new on the bottom. So again, I'm going to cross multiply and divide. That's all I have to do. So 12 times 6 is what? 72 divided by 9. That means C prime is equal to 8. And that I know you have done because I taught quite a few of you how to do that in 7th grade. Okay, that is finally it for chapter 10. And again, I know there are lots of little subjects, lots of little problems. We're just going to have to do the best that we can with a whole bunch of little bits of information. So homework 10B. We will cover 10A and 10B in class. I'll answer questions. We can even work through the whole assignment if you would like to. But do what you can at home. The rest we'll cover tomorrow in class.